Hello and welcome to another video on algebraic proof with quadratics, and this is going to be the last video in this series on algebraic proof. So this statement here, it says prove that the difference between the squares of any two consecutive integers is equal to the sum of the two integers. Now at the moment that might sound a bit of gobbledygook, but let's just take it step by step. So the difference between the squares of any two consecutive integers. So first of all, let's have a look at this statement here. Any two consecutive integers. Well, if we think about n as an integer, then the integer after n, the consecutive integer, would be n plus 1. So for example, our two consecutive integers could be 6 and 7. So n would be 6, and here we'd have 6 plus 1, which is 7. So these would be our two consecutive integers. Now let's have a look at the bit before that. It says the squares of any two consecutive integers. So we need to square these two numbers. So if we square this first integer, well, we're just going to be left with n squared. And now if we square this second integer, that's going to be n plus 1, all of that squared. Be really careful with this because this is not n squared plus 1 squared. It is n plus 1, all of that squared. So we could rewrite this as n plus 1 times n plus 1. Now to expand this out, we could use the grid method, but just for quickness, I'm going to use the FOIL method. So we're going to multiply everything in this bracket by everything in this bracket. So we're going to do n times n, which is n squared, n times 1, which is 1n, and then we're going to do 1 times n, which is again 1n, and finally 1 times 1, which is 1. So when we expand this out, we get this expression, but then we can simplify this. So this becomes n squared plus 2n plus 1. So now we have squared both integers. And finally, it says the difference between the squares of any two consecutive integers. So we need to find the difference between these two numbers. So to find the difference between the two, I'm just going to take this expression away from this expression here. So I'm going to do n squared plus 2n plus 1, and I'm going to take away n squared. That will give me the difference between the two numbers. So we can just simplify. N squared take away n squared. Well, those two terms will just cancel out with each other. And all we're left with is 2n plus 1. So let's go back to our question. It says prove that the difference between the squares of any two consecutive integers is equal to the sum of the two integers. Well, this is the difference between the squares of any two integers. So is it equal to the sum of the two integers? Well, the sum of the two integers are just these two integers added together. That's what sum means. So if we add these two integers together, we get 2n plus 1. And they are equal. They are exactly the same. So we have proved our statement. Okay, so what I'd like you to do now is pause the video and see if you can prove these two statements here using algebra. Okay, so let's go through these together now. So the first one, it says prove that the sum of the squares of any two consecutive even numbers is always a multiple of 4. Now again, it's quite long-winded, so let's break this down. So first of all, let's have a look at any two consecutive even numbers. Now hopefully after watching one of my previous videos on this topic, you know how to write down two consecutive even numbers. And the key thing to recognise is that any even number is always a multiple of 2. So to write our first even number, we can just write 2n. Okay, it doesn't matter what the value of n is, as long as we multiply by 2, this will always be even. Now, it says two consecutive even numbers. So what is the next even number going to be after this one? Well, the next even number, we just need to add on 2. So our next even number is going to be 2n plus 2. So these are our two consecutive even numbers. Now let's have a look a bit before. It says the sum of the squares. Well, first of all, let's just have a look at the squares. So the squares of these two numbers. Well, we just need to square both of these numbers. So if we square our first integer, that's going to be 2n squared. Well, 2 squared is 4, so it's just going to be 4n squared. Basically 2n times 2n is 4n squared. Now let's square our second integer. And again, what I'm going to do is I'm going to rewrite this as 2n plus 2 times 2n plus 2. And I'm going to do it over here because I can see myself encroaching on this question over here. And again, let's use the FOIL technique. So 2n times 2n, or that is 4n squared. 2n times 2 is just plus 4n. 2 times 2n is again 4n. And 2 times 2 is plus 4. And we can simplify this just before we go any further. So we can combine like terms. So it's going to be 4n squared. And then if we add these two terms together, we get plus 8n, and then we've got plus 4. So 2n plus 2, all of that squared, is this expression. And now the final part is to calculate what the sum of the squares of any two consecutive even numbers are. Well, we found those two numbers. Now to find the sum of them, we just add them together. So we've got 4n squared plus 4n squared plus 8n plus 4. And we can simplify that again, so we can combine the n squared terms. So we are left with 8n squared plus 8n plus 4. Now we need to prove that this expression here is always a multiple of 4. Now how do we do that? Well, we can see that we can factor out a 4 from each term in our expression. Each of these terms is divisible by 4. So let's factor out a 4. So when we factor out a 4, what are we left with? Well, 8n squared divided by 4 is 2n squared. 8n divided by 4, well, that is 2n. And finally, 4 divided by 4 is 1. And we are done. This expression here is a multiple of 4 because, again, it doesn't matter what's inside our brackets. On the outside of our brackets, we have a 4. So we know that whatever we've got, we are multiplying by 4. So we are done. Okay, let's move on to the next one. Prove that when any odd integer is squared, the result is always one more than a multiple of 8. So, when any odd integer is squared. So, well, first of all, what is an odd integer? So if we say that 2n is an even integer, well, to make this an odd integer, we just need to add on 1. So any odd integer, we can write that as 2n plus 1. So when this odd integer is squared, so we need to square this integer. So we're going to take 2n plus 1 and we're going to square it. So again, I always like to write it out in full. And again, same as before here, I'm going to expand the brackets using the FOIL method. And now let's go back to the question. It says prove that when any odd integer is squared, which is what we've got here, it is always one more than a multiple of 8. Now you may be wondering how on earth you prove that this is always one more than a multiple of 8. Well, we've already got that one more than here, so that would be the one more than bit. So if we can prove that this is a multiple of 8, then we can prove that this whole thing is one more than a multiple of 8. So let's focus on 4n squared plus 4n. Now what can we factor out from 4n squared plus 4n? What is the highest common factor of both terms? Well, we can factor out a 4n from both terms. So if we factor out a 4n from both terms, in our brackets we are just left with n plus 1, because 4n squared divided by 4n is n, and 4n divided by 4n is 1. Now, how do we prove that this is a multiple of 8? Well, if we just think about if n is even and n is odd, and if we can prove that in both situations we get a multiple of 8 both times, then this is always going to be a multiple of 8, because you can only have odd and even integers. Okay, we're excluding 0 in this scenario. So first of all, let's think about when n is even. So if n is even, well, this is going to be a multiple of 8 straight away, because the smallest that n could be is 2, and 4 times 2 is 8, but then we're always going to have multiples of 8 the bigger n gets. So if n is even, 4n is always a multiple of 8, and then it doesn't matter what's in this bracket. As soon as we're going to multiply by 8, this whole expression is going to be a multiple of 8. So we've looked at when n is even. Now let's think about when n is odd. So if n is odd, n plus 1 is going to be even. So this inside the bracket is going to be even. And now if we're saying that n plus 1 is even, well, an even number times 4 is going to be a multiple of 8. So just to summarise, if n is even, this whole expression is going to be a multiple of 8. And if n is odd, this expression is also going to be a multiple of 8. So it doesn't matter if it's even or odd, this expression will always be a multiple of 8. And then if we are adding on 1, because remember this part here is the same as here, we're adding on 1, remember, so we need to add on that 1. So if this whole thing is a multiple of 8, this whole expression is 1 more than a multiple of 8. And we are done. So hopefully you followed my logic throughout those last two examples. They are quite tricky to grasp. But my advice for you when proving statements like this is to just take each step at a time, because these sentences are quite long and it can look quite confusing. But if you take each part one at a time and then put them together right at the end, it does make things a lot easier. Now that's going to be the last video on algebraic proof. So if you get stuck at any part, go back through my playlist on this topic, and hopefully that helps. See you soon.